static loading. So there is a force, it's constant, or there's a moment, it's a constant, it's not fluctuating. Next chapter, we'll look at fluctuating loads. So most centrally, we are interested in what are known as failure theories. So imagine something is loaded, let's say a bridge, and that bridge is, if you see a bridge, it will say it's rated for so many pounds or so many tons, right? How do they come up with that number for the tons this particular bridge can take? And you can come up with a number provided you understand why a material fails. And how can we predict failure? So this goes back to the material in question. If you build something of steel, it'll fail differently from something which is brittle, right? Steel is ductile, and something else could be brittle, and then they will have different characteristics. Luckily, there are not too many types of materials. We'll only be looking at materials which are ductile or brittle. This is sort of a review of what we've seen for these materials. So it's kind of interesting that we do tests in the lab, pretty much tensile loading tests, use the stress at which things fail, and use that to design more complex things like bridges or machine elements, like elements in say a lathe or so any mechanical element. So what we do is we look at the stress strain curve, which we've seen quite a few times now. So that curve looks something like this for ductile materials. There's a point at which the material will yield. It will not be linear. There's a point at which it will fail. There'll be, necking. S. So that's the maximum strength, SU. And then SF is where it fails. On the other hand, for brittle materials, the curve pretty much stops abruptly. It just goes up and just stops. That strength at which material fails, breaks, is either characterized by SU or SF. So let's have this E. No, sorry. This should just be EF. Okay, so for ductile materials, typically the strain at failure is greater than 0.05. And for brittle material, strain is less than 0.05. In other words, what it's saying is that ductile material can take more strain before failure than brittle materials. So we've also seen that SU, SF are the strengths for necking, where there's a maximum in the curve for ductile materials. Those are distinct. And SU, SF are the same. Then finally, what we do is we have to basically make up a theory which will predict failures. And what theory we make for this is totally something, it's not like Newton's laws where F equals ma is true for no matter what the object is. Of course, if you're going too fast, then F equals ma does not hold in this theory of relativity and so on. But we don't have that kind of unique relationship for failure theories. There's not one theory which would explain all the breakages. And so what we do is we come up with a criterion for failure and then observe how things fail. And then if it works for many materials, we say that that's the theory we're going to use for those materials. And if it fails in a different way, then and we come up with a new theory, then we'll use that. So what we're going to do is we're going to assume that we can design materials based on failure is based on SY, the yield strength. Okay, and here we'll assume that failure is based on SF, which also some people like to use that as a value for SY. It doesn't really have, just put SF for now, and then we can change that. We'll talk more in detail about that a little bit later, but let me just put it SF. Okay, so as I said, these theories are what we think how things will break, and they're all empirical things, which means that they're not universally true, unlike some of the laws of motion, as an example. So people have come up with a lot of theories, and I'm just going to list down 3 theories for ductile materials, 3 theories for brittle materials. Once you come up with a theory, you test it by loading something to failure, and then see if that theory holds true. So here are some theories of failure. For ductile materials, the most dominant theories are these. One, and we'll go through each of them one at a time. Maximum shear stress theory. It's also more commonly known as MSS. We have the distortion energy theory, DE. Third one, ductile Coulomb Moore, also known as DCM. Okay, so these are just a sample of the large number of theories out there. I'm listing these, and we'll study these because they are the ones which are most commonly we've seen materials of interest, like aluminum, steel. They typically follow these theories. Within a particular element, material like aluminum, there would be various grades of aluminum. So that's why we need to have not one, but multiple of them. Then we have brittle materials. So we have a maximum normal stress. It's also abbreviated as MNS. There's the equivalent of the Coulomb-Moore theory for brittle materials called the brittle Coulomb-Moore theory, or BCM. And then finally, modified Moore theory, MM. Okay, so my goal is to go through each of these theories, and then we will see how we can apply these theories to predict failure. And then once you introduce a factor of safety, you can also design materials based on these various theories of failure. Okay, so let's get started. The first one, maximum shear stress theory. Okay, so what's this theory? It says that the material yields when the maximum shear stress equals or exceeds the maximum in a drop my internet in a tension test specimen of the same material during yielding. Okay, so let's just dissect what this theory says. So the key thing is maximum shear stress, okay, equals or exceeds the maximum shear stress in a tension test specimen, then equals or exceeds. Okay, the first part in red means that you're given a specimen which some specimen is subjected to a load P1, P2, M. What you need to do is compute sigma max, or sorry, tau max. Okay, so for example, when we had a beam which is subject to bending moment, we can then use that to find the normal stresses and the shear stresses, and from that find the principal stresses. So there's a principal stress and there's a principal shear stress. That's the shear stress we're after. So we compute that for a general loading. Then what we'll do is we'll find the corresponding. So the blue thing is you want to compute. Use a tension specimen, subject that to a tensile force. And let's say it begins to yield when it'll yield when the stress is SY, right? Yield strength. Okay. Now we'll compute the maximum stress in this case. So the normal stress is SY. What is the maximum stress? Compute tau max prime. So given this yield strength, how do you compute tau max prime? One way to do it is to use transformations. That is the plane stress transformation formulas I give you. The other way is to use Morse circle. I'll just use Morse circle. It's much easier. So we're looking at a specimen which has just these stresses. So if you draw the Mohr circle, okay, sigma y is 0. Sigma x is sy. Okay. So then we have to draw the center of the, so those are the 2 points which are on the diameter of the circle, right? Now we need to find the center, which is basically midway. And then we need to construct a circle which passes through 0 and sy. And so the maximum stress is nothing but sy divided by 2. So tau prime max is equal to sy divided by 2, just from the Mohr circle. You could also use transformation. So for this, we know the maximum stress in red. That's the stress we get from that complicated loading condition. We got the maximum stress from the uniaxial tension test. And now the thing we need to do is check for failure. This happens when tau max in red is greater than or equal to tau prime max, or sy divided by 2. That's the failure theory. Failure condition is when tau max exceeds tau prime max, which is sy divided by 2. Okay, so then the question is, why are we even thinking of shear stress to build a theory for failure? Why should it be the shear stress? Why not the principal stress, right? Why not use, for example, why not use this stress? Why use this stress, which is the maximum stress? It's because of an observation people make when they do this tensile test. So why tau max? Okay, so then what people have observed is when they take this specimen, which I've drawn in the past, and load it. So when they keep increasing the load P, they observe that the specimen necks down, that is basically the diameter is going to decrease, the length is going to increase, and eventually it will break. When they look at the specimen which broke, they see that it actually breaks at an angle of 45 degrees. For many material, it does break like that. It just actually breaks at 45 degrees. Yeah, so answer is not all the time. Only many materials show this. Okay, and when people saw that it breaks at that angle, they asked the question, what stress is maximum at that angle at 45 degrees, right? It's the shear stress, because remember that when it's at 45 degrees on that plane element, it is at 90 degrees on the Mohr circle. So this is like saying, if there's a specimen, if it's loaded like so, then at 45 degrees, we would have we'll have shear stress. So let me draw it this way, which will be sigma divided by 2, and then normal stress will be sigma divided by 2. Same thing. So it's just that observation made people think that that should be a good theory because of what we observe. Okay, again, this is a empirical science. There's no universal laws. This is what you observe. This is, let me make a theory from that. But this is also the plane for maximum shear stress. Okay, so that's the theory. Now let's see how we can use this theory, which is right here, in order to make some predictions for 3 dimensions, which usually is very important, right? And then how do we incorporate this theory in designing a material element? So in 3D, this is what you will do. So how to apply this in 3 dimensions? Okay. Remember, in 3 dimensions, we'll have 3 more circles. So there would be a bigger Mohr circle and 2 smaller Mohr circles, and they would actually intersect each other or circumscribe each other in the way shown. So there are stresses. Let's move that down. So in 3D, we'll have 3 stresses. Let me call that sigma A, sigma B, sigma C. Okay, what we do in 3 dimension is renumber them or renumber them such that sigma 1 is greater than sigma 2 is greater than sigma 3. Once you do that, sigma 1 is this, sigma 3 is this one, and sigma 2 is there, right? Just because this is the sigma axis, and then the maximum is clearly from the figure, sigma 1. Okay, so then what we'll do is we'll find the maximum shear stress, right? How many shear stresses are there for 3 more circles? There are 3 maximum shear stresses. There's one for this. Let me just put this somewhere else. Okay, here's another maximum shear stress, and here's the third maximum shear stress. Maybe it's not right here. Maybe its center is here. Okay, out of these 3 red lines, which are the 3 maximum shear stresses for the 3 circles, you can see that the maximum one is the one for the biggest circle. This is the one which determines failure. So what you'll do is you'll use that one to compute the maximum shear stress. Let me call that tau, in fact, tau prime. So tau prime max would be, if you remember, tau max is simply the radius of the circle, like I've shown there. It's nothing but sigma 1 minus sigma 3 divided by 2, right? Because sigma 1 and sigma 3 are the endpoints or the points on the diameter. So that's how you'll get sigma prime. Sy comes from your uniaxial test. So failure criterion is as follows. tau max prime is greater than sy divided by 2, or sigma 1 minus sigma 3 divided by 2 is greater than sy. Some people like to keep it that way, or simplify it to sigma 1 minus sigma 3 is greater than sy. So if you know the maximum, the minimum principal stress, and if you know the yield strength, this basically is a formula which determines failure. Okay, that's how you do it in 3D. Now, how to use this equation for design, right? Because you don't want something to fail. So then we'll basically over design it such that the stress tau max never exceeds sy divided by 2 by a certain factor. So here in this case, you're just making them equal. But what if you design tau max to be less than half of sy divided by 2? So that half in that case would be 1 divided by the factor of safety. So for design, we'll basically do this. How use failure theory for design. We'll simply define a factor of design factor. Design factor or factor of safety. ND or N, it's equal to max stress, shear stress, allowable stress. That's the definition. So the max stress would come from the uniaxial test, so that would be tau prime max. And then allowable stress would be tau max. So NT or N equals sy divided by 2, sigma 1 minus sigma 3. So the factor of safety just ensures that your maximum stress, tau max, never exceeds tau prime max by that factor. Yeah. Yes. Okay, so for 2D, one stress is always 0. Okay, so an example would be if you get, so if it's a plane element which doesn't have a third dimension is relatively small, or the stress in the third dimension is 0, and if I given the stresses as follows, sigma A equals 5, sigma B equals -3. Remember, these stresses comes from the Mohr circle, or if you have the plane stress element, you can then use those transformation equations to find the principal stresses, and those are the principal stresses. So in this case, what you'll do is you'll convert that to a question. One stress is always 0, yeah. So in this case, the two stresses are these stresses they need not be 0. But the third stress you need to take as 0. That's where the logic is. Then arrange them in ascending order. So sigma 1 is greater than sigma 2 is greater than sigma 3, which would be 5 is greater than 0 is greater than -3, right? So this is sigma 1, this is sigma 2, this is sigma 3. So in this case, ND or N equals Sy divided by sigma 1 minus sigma 3, which will be Sy divided by 5 minus -3. So this is just, if you're doing a calculation, then this is what you will do. You will write down, you'll first arrange them in descending order, and then use sigma 1 to be the maximum, sigma 3 to be minimum.
Professor, I have a quick question.
Yeah.
Why are we doing arranging them in descending orders?
Because of this, which is, we are trying to treat 2D case as a 3D case. In fact, it's a special case. You'll always have 3 circles in 3D. So when you add the second 0, then you'll also get 3 circles. The one which determines failure is basically the radius of the biggest circle. So in this case, the biggest circle is here, which is determined by the maximum principal stress and the minimum principal stress. So you always have to arrange them in the ascending or the descending order, such that you identify sigma 1 and sigma 3. So now if you have a case where you have 5 minus 3 and nothing is given for the third one is 0, which means that this one is max and this one is minimum. And then this will be sigma 1, this will be sigma 3. So here this might make it more clear. Let me have another example where you'll see that. Example 2. So let's assume that you have a plane stress element, and then you computed the principal stresses, and you get the following. You get sigma A equals 5, sigma B equals 1. In this case, you'll assume sigma C is 0 because it's a 2D case. So now sigma 1, so we need to arrange in descending order. So sigma A is greater than sigma B is greater than 0, or in other words, 5 is greater than 1 is greater than 0. So this is sigma 1, this is sigma 2, this is sigma 3. And now your equation for design would be Sy divided by sigma 1 minus sigma 3, 5 minus 0. Okay. We can also do this with Morse circle, which is, so this is one stress, sigma 1. Sigma B is here. Put it closer to the axis. This is sigma C. And then sigma A equals 5. Okay, so I need to draw more circles now with these 3 dots. So one of them would be this one. One of them would be like this. And the third one would be like so. And then if you want to figure out the maximum stress, it's going to be right here. Okay, what is this? It's basically 5 minus 0 divided by 2. And that's why you'll use 5 minus 0 here. So that factor 2 cancels because there's Sy divided by 2. Okay, so that's how you basically always draw 3 more circles to do this. Just because they have a 2D case, you cannot just use the 2 non-zero stresses to figure out the maximum shear stress. You need to account for the third one. So in this case, the critical stresses are actually sigma C. The critical stresses are this one and this one. While in the previous case, the critical stresses were this and this. Just note that it's A and B, not C, but here it is A and C, not B. So this is actually a common mistake people make. They just take whatever they get from 2D case to solve for maximum stress. Okay, one last thing, and then we'll stop. I just wanted to do this nice plot which shows how these stresses, we did this calculations, I showed you a number, but you can actually represent the area which represents a safe region from these equations. So that won't take time, quickly do it. So in 2D, this is what we're going to do in 2D, not for 3D. So let's say we got 3 stresses, sigma A, sigma B, and sigma C. Okay, just like the previous one, I put some numbers, but I'm just going to do a generic case. Let's assume that let's say that sigma A is greater than sigma B is greater than 0, right? One of them is going to be 0. Let's say that third one is 0. Yes. So the second case is, okay, so my bad. Okay. So if sigma A and sigma B are greater than 0, then the failure is determined by Sy equals sigma 1 minus sigma 3, right? So we need to arrange this. Will be sigma 1 is sigma A, and sigma 3 is 0, right? The minimum one. Okay, so that keep that as it is. Next, let's assume sigma A is greater than 0, is greater than sigma B. In other words, the stress sigma C is 0, which is the middle one, and sigma B is less than 0. So in this case, failure will occur if Sy equals sigma 1 minus sigma 3, which would be sigma A minus sigma 3, in this case is sigma B. And then one more case, sigma A, 0 is greater than sigma A is greater than sigma B. In other words, sigma C is now the biggest stress, and sigma A and sigma B are less than 0. So your failure will occur when Sy equals sigma 1 minus sigma 3, which would be 0 minus sigma B. Because sigma 1 is 0, sigma 3 is. So if you take all these things, all these cases, you can actually do a plot. And I'll go maybe 1 minute over time. I'm just going to show the plot formed by equations 1 to 3 using equations 1 through 3. We have the following plot. Sigma A, sigma B, Sy. Okay, you can show that those equations I wrote down, 1 through 3, basically form, I would say, sort of like a hexagon. And the area within the hexagon is the non-failure region. So as long as your stress is in that yellow region, material will not fail. And this is only possible for 2D. This figure in 3D is much more complicated. So I'll stop here.